derivatives. So there are much topic of application of derivatives, but for now, let's focus only in the instantaneous rate of change and geometrically as the slope of a tangent. There are essentially two ways to interpret the derivative as instantaneous rate of change and geometrically as the slope of a tangent line. When translated as instantaneous rate of change, it tells us how quickly a function is changing at a single value of an independent variable x. An example of that is a speedometer. The reading in a speedometer tells you how fast you're changing of position roughly at that particular instant of time. Imagine you start at the time t equal to 0 and after 15 minutes into the journey, the speedometer reads 40 miles per hour. Now that's your instantaneous rate of change of position with respect to time at t equal to 15 minutes or 0.25 hours. It's written as dp over dt followed by a vertical line and down in the subscript t equals to 0.25 hours where p stands for the position. To make it clearly, I will show you the formulas and give some another example. The derivative of a function f at a specific value of x says a is the value given by f prime of a equals dy over dx equals lim h approaches to 0, f of a plus h minus f of a over h. And the derivative of a function f as a function of x is called f prime of x is given by f prime of x equals dy over dx equals lim h approaches to 0, f of x plus h minus f of x over h. So let's have our example. Find the derivative of f of x equals 3x squared negative 4x plus 7. So this will be our f of x plus h and this will be our negative f of x. In our solving, we find that the f prime of x equals 6x minus 4. Another application of derivative is to find the equation of a tangent and a normal at a point in a curve like I mentioned in the beginning. The geometric interpretation of a derivative at a point is the slope of a tangent at that point, usually denoted to a small letter m. If we know the slope of any straight line as well as the coordinates of any one point on it, then the equation of that line can be found by the point-slope form. I'm talking about this popular form y minus y1 equals to m times x minus x1. Her x1, y1 are the coordinates whose values are known to us. And m is the slope of the line. In our case, the derivative is the slope. And the known coordinates will be x1, f of x1, the point where the tangent touches the curve. The equation of a tangent at x1 will then be y minus f of x1 equal to f prime of x1 times x minus x1. In a similar way, we can find an equation of the normal line which is perpendicular at this tangent at the point of tangency. So that's all guys, I hope that you learned our topic for today. Thank you for watching and see you soon to our next video.